This is a production of the Chemical Education Material Study.
This is oil, the way it comes out of the ground. Most of it is used in fuels, but chemists take oil like this and change its chemical composition to make thousands of new organic compounds. The preparation of a new chemical compound from an existing compound is called synthesis. Professor Geisman will carry out a typical synthetic operation. He will transform 2-butanol, an alcohol, into a solvent used, for example, to clean computer disks, called 2-butanone, a ketone. The key reaction in this synthesis is the oxidation of an alcohol functional group into a carbonyl group. The carbon skeleton remains the same. Only the functional group changes. To accomplish this change, we use an acid solution of sodium dichromate. In the reaction, the orange dichromate ion will be reduced to dark green tripositive chromic ion. The reagents will be mixed together in this reaction flask, where the alcohol will be oxidized to the ketone. This is the synthesis. Purification of the ketone will be done with this distillation equipment. The identification of the product ketone will be confirmed by infrared spectroscopy and by nuclear magnetic resonance spectroscopy. Synthesis, purification, identification, key steps in making any new organic compound. As a first step, Dr. Geisman assembles the apparatus and the reagents. But how much of each reagent will be needed?
To find out, we first write a balanced equation for the reaction. This is the way we do it. We start with the structural formula for 2-butanol. The products of the oxidation are the ketone, plus 2 hydrogen ions, plus 2 electrons. This is the half reaction for the oxidation of the alcohol.
Here, the other half reaction has been added to give the net equation. 3 moles of butanol are oxidized to butanone, while 1 mole of dichromate in the presence of acid is reduced to chromic ion. With this, we can calculate the amounts of reagents that will be needed. 2-butanol has this structure and a molecular weight of 74. For the size of the apparatus we shall be using, 1/2 mole of butanol will be a convenient amount. Let's base our calculations on that amount. 1/2 mole, then, will be half of 74, or 37 grams. Now for the procedure. First, weigh the empty beaker and set the balance for the 37 grams determined by the calculation. Professional chemists use many safety precautions. However, in our process, equipment and chemicals are of such little hazard compared to the skill of the professional that glasses are not worn. In school labs, where someone else's mistakes can be dangerous to you, glasses should be worn at all times. Do note the great care and careful techniques Professor Geisman uses. Next, calculate the amount of sodium dichromate that will be needed. and measure out the required amount. Then measure out the amount of sulfuric acid required by the equation as the source of hydrogen ion. Geisman has now determined and weighed out the amounts of the 3 reagents needed in the synthesis. Dilute the sulfuric acid with water. This must be done carefully by pouring the acid into the water while stirring constantly. Note that the heat of reaction vaporizes water, which condenses on the side of the beaker. To the sulfuric acid and water, add the sodium dichromate. This gives an aqueous acidic solution of the oxidizing agent ready to be used in the reaction. Before adding the reagents to the reaction flask, Geisman uses diethyl ether to dissolve the butanol. The amount of ether added to the butanol is not critical because ether is not consumed in the reaction. Rather, the ether dilutes the reaction mixture so that the rate of reaction can be more readily controlled. Also, the product ketone is much more soluble in ether than in water. This property will be helpful in the purification stage. Now that the solution of butanol in ether is ready in the reaction flask, the orange-colored oxidizing solution made from sodium dichromate, sulfuric acid, and water is poured into the dropping funnel. Ether and water do not dissolve appreciably in one another, so a mechanical stirrer is used to ensure that the 2 solutions will mix well enough for the reaction to take place. Add the dichromate solution to the flask at a controlled rate. The oxidation begins, releasing heat. The heat is absorbed by the water bath around the reaction flask. As the reaction proceeds, the color changes from the orange dichromate ion to the green chromic ion. The flask now contains the ketone product, plus some inorganic materials and the solvents. The actual synthesis is now complete. How is the ketone purified from this reaction mixture? The first step in the purification of the 2-butanone is to place the reaction mixture in a separatory funnel. The ether and substances soluble in it gather in an upper layer. This is hard to see now, but will become more visible as the purification continues. The water and substances soluble in it, including most of the inorganic material and a small amount of the product ketone, settle into a lower layer. When this aqueous layer has completely settled, it can be drawn off. The last of the aqueous layer is coming out. There. Most of the desired product ketone is in this remaining ether solution. Set it aside for now. The aqueous layer is returned to the funnel. A further portion of fresh ether is added to extract any ketone still dissolved in the water, as the ketone is much more soluble in ether than in water. The ether again forms a layer on top of the aqueous layer. The ketone moves readily from water to ether, as shaking provides a large surface area. Open the stopcock from time to time to relieve the pressure due to vaporizing ether. Again, allow the layers to separate and draw off the aqueous layer. Several such extractions with fresh ether remove virtually all the ketone from the aqueous layer which is discarded. All the ether extracts now go back into the separatory funnel. The synthesized ketone is in the ether solution. This solution contains the desired product, 2-butanone, ether, traces of the sulfuric acid, and some of the inorganic materials used in the synthesis. Now, continue the purification. First, neutralize the traces of sulfuric acid with an aqueous solution of sodium hydrogen carbonate. The bicarbonate reacts with the sulfuric acid to form a gas, carbon dioxide, which is allowed to escape. As before, the aqueous layer will be drawn off after it is settled. Then add distilled water. Repeat these washings to remove all traces of inorganic ions, ending up with this nearly clear liquid above the aqueous layer. Draw off the final water wash. The remaining ether solution contains some traces of water from the washing operations, as shown by the slight cloudiness. To absorb these traces of water, place solid anhydrous sodium sulfate in contact with the ether solution. A clear, dry ether solution of the ketone product remains. Now the ketone will be separated and purified by distillation. Remove the solid drying agent from the ether solution by filtering the solution into a distillation flask. These small boiling chips of porous material promote the formation of bubbles and help the solution boil smoothly. Notice the electric heater. Ether vapors are highly flammable, so no open gas flames are used because of the danger of fire. The solution does not take long to boil. The boiling point of pure diethyl ether is 34.6 degrees Celsius. The ether vapors condense in a water-cooled coil and collect in this receiver. Eventually, the temperature starts to rise above 35 degrees, so most of the ether must have been distilled. The material remaining in the distillation flask is the ketone plus residual ether. This smaller apparatus will minimize loss of material during a second and final distillation. The boiling point of the ketone is listed in the handbook as 79.6 degrees Celsius. However, when the temperature nears 35 degrees, the first material coming off is the residual ether. As distillation continues, a ring of condensing ketone vapor rises through the column and surrounds the thermometer bulb. The temperature increases rapidly. At this point, change the receiver and attach a previously weighed flask. The temperature becomes constant just below 80 degrees. This indicates that the purified ketone is distilling and collecting in the receiver. The second stage, purification, is now complete. The flask is weighed to determine how much ketone has been obtained in the synthesis.
The actual yield of our ketone is 30 grams. What is the maximum amount of ketone we can obtain starting with 37 grams of the alcohol? Let's see. The oxidation of 1 mole of alcohol, 74 grams, will yield 1 mole of ketone, 72 grams. Therefore, 37 grams of alcohol could have given a maximum of 36 grams of ketone. The amount of ketone we actually obtained was 30 grams. The result of a preparative experiment is usually reported as a percentage yield. The actual yield, 30 grams, divided by the theoretical yield of 36 grams, gives us 83%, the percentage yield. This is a reasonably good result. Yields as good as or better than this can often be obtained if one is careful in controlling the conditions of the reaction and in isolating and purifying the product.
How do we show our product is the same as this known sample of 2-butanone? Here is one identification procedure. Pour the known sample of the ketone into a small container and then into a cell which fits onto an infrared spectrometer. This instrument measures the infrared absorption spectrum of the sample. Compare the spectrum of the known sample of the ketone to the spectrum obtained from the product of our synthesis. The curves match, so the two materials are the same, and the synthesized product is identified. Nuclear magnetic resonance spectroscopy, called NMR, is another way to identify a compound. The newly synthesized material is placed in a magnetic field. NMR is especially useful when a previous sample of the product is not available for direct comparison. Often, using NMR, only the empirical formula may be needed to deduce the full structure. This type of spectroscopy measures the absorption of radio waves by nuclear magnets placed in a strong magnetic field. Protons, like the ones in the 2-butanone, are nuclear magnets, and the energies they absorb are characteristic of their chemical environment. We know the empirical formula of 2-butanone is C4H8O. What is the structure of the material we have synthesized? This highest spectral peak shows that there is a CH3 group separated from any other hydrogens. This set of peaks shows a CH3 group next to a CH2 group. And these peaks show a CH2 group next to a CH3 group. These three groups add to C3H8. As the empirical formula for the molecule is C4H8O, there are a C and an O unaccounted for. Together they constitute a CO group, which does isolate one CH3 group. So the overall structure is identified as 2-butanone. As you can see, NMR is a powerful method of determining structure. These are the key steps in creating new compounds for scientific study and for practical application. Almost everything you buy, colas, burgers, calculators, plastics, medicines, cosmetics, clothing, and many other things result from the processes of synthesis, purification, and identification.